So today, we'll talk about factors affecting equilibrium. So once a reacting system has reached equilibrium, it remains at equilibrium until it is disturbed by some change of a condition. A guiding principle is also known as Le Chatelier's principle. Le Chatelier's principle says that if you induce a stress on a system at equilibrium, the equilibrium will shift so as to relieve that stress. But before that, let's recall what equilibrium means. Chemical equilibrium exists when two opposing reactions occur simultaneously at the same rate. So, this means that the forward reaction and the backward reaction occurs at the same rate. So, this arrow is supposed to be a double arrow. The double arrow indicates that it is a reversible reaction. It can go forward or backward, but both reactions occur simultaneously. The capital letters represents the chemical formulas, and the lowercase that appears on the left side are called the reactants, while the ones on the right side are called the products. So, again, this is the reactants, while this is the products. The reaction can proceed in either direction. When A and B react to form C and D at the same rate at which C and D react to form A and B, then the system is at equilibrium. So, I mentioned a while ago that if you add stress to the system, that system will shift in the direction that will reduce the stress. So, there are three known changes that will affect the system at equilibrium. When you apply a stress to a system, after some time, a new equilibrium will be established. The reaction quotient, or Q, helps us predict the direction of the shift. There are three types of changes that can disturb the equilibrium of a reaction. Number 1 is a change in concentration, and number 2, change in pressure or volume, and number 3, change in temperature. First, the type of change in the change in concentration. Let us consider the following state system starting at equilibrium. So, when more reactants or products is added to the system, the value of Q changes so that it no longer matches the Kc. So, Q is equal to C, concentration of C, times concentration of D, all over concentration of A, multiplied by the concentration of B. The stress due to the added substance is relieved by shifting the reaction in the direction that consumes the added substance, moving Q back to Kc. Knowing this, we can predict the shifting of the reaction. So, let's see what happens if we increase or decrease the products or the reactants. Once again, these are the product side. Once again, let's see what happens if we change the concentration of the products or the reactant sides. Once again, this is the product side. Once again, let's see what happens if we increase or decrease the concentration in the products or in the reactant side. Once again, this is the reactant side. This is the product side. So what happens if we increase the concentration of A or B? Q is less than K, meaning the direction of the shift goes right. And when we increase the concentration of C, or D, Q is greater than K, meaning the direction will now go left. Now what happens if we decrease the concentration of A or B? Q will not be less than K, but is now greater than K, meaning the reaction will shift left. And when we decrease C or D, Q will be less than K, meaning the reaction will shift right. Remember, changing the concentration changes Q and Q only. It doesn't change Kc. The second type of change is the change in pressure and volume. This change affects only gases, since gases are compressible and solids aren't. One thing we have to remember is that an increase in volume is a decrease in pressure. So an increase in volume is a decrease on pressure, and vice versa. But how do we correlate concentration to pressure and volume? Now, you have two balls. Each of the balls has the same space and the same number of balls, meaning they occupy the same space, they have the same concentration, since the ratio of space and the number of space occupied is the same. But what if we have the box? As you can see, the space left is much smaller than the original. This means that the concentration of box 1 increased. While the concentration. Now, what if we make the box 2 times bigger? If this happens, the concentration of box 2 decreases because there are more space to occupy. So, once again, if a volume decreases, pressure increases. And if this happens, Q is greater than Kc. And the direction of the shift will go towards the smaller number of moles of gas. While if volume increases and pressure decreases, Q is less than Kc, and the reaction or the shift in reaction will go towards the larger number of moles of gas. So the last type of change is the change in temperature. For an endothermic reaction, heat is a reactant. So by increasing the temperature, you are essentially adding more heat, therefore adding more reactants. So increasing the temperature will mean that you are also increasing Kc. Now if you decrease heat or temperature, Kc will also decrease. Now for an exothermic reaction, if you increase temperature, Kc will decrease. But if you decrease the temperature, Kc will increase. So that's the end. Le Chatelier's principle, factors affecting equilibrium. Remember, catalysts do not affect equilibrium. They only speed up the reaction.